All right, let's talk about the second part of lecture 9, where we're going to do more proofs about sets. Before we go through problems, there's a few tips about learning in CS 2100. Number 1 is to read your textbook. Number 2 is to watch the pre-recorded lectures, read the pre-lecture and after-lecture slides, try to do the lecture problem sets before the actual recitation. Of course, attend recitations on Tuesdays, discussions on Thursdays, and actively participate during those classes. And if you have additional questions, please go to TA or instructor office hours. We have office hours every day of the weekday, and please use Piazza for Q&A. Especially for induction proof, try to put some structure in the proof. For example, problem statement, base case, induction hypothesis, and induction statement. Okay. Finally, in order to prepare for quiz number 2, please try to, and of course later for quiz number 3, we're going to see a lot of proofs. Please try to review some of those algebra foundations. And some of the problem indeed require a bit of reverse engineering in the proofs. All right, let's do a quick review. This is a question we've seen in part 1 of lecture 9. But again, let's quickly do this one more time. So the idea is to use various properties involving sets. For example, things like commutative, associative, distributive, identity, and negation type properties to prove the statement. Okay. Again, we're going to follow similar rules to go from left to right. When I have A union A complement, A intersect B, what you do is you're going to do, first of all, this looks like distributive rule right here. So you're going to use distributive rule where A union A prime, A union B, and then their interaction is intersection. And now the next thing you're going to see is A union A prime, which if you look at the rule, it's using negation rule, it's going to equal to the universal set. So this is equal to a universal set, intersect A union LB. Okay, this is using negation. The next one you're going to do is you are going to do some sort of shifting of the ordering using commutative rule. Commutative rule. So you get A union B intersect U. And now, because you are taking a set and you are intersecting with the universal set, then what you will get is the identity rule. If you intersect a set, intersect universal set, which is all the possible element, is a set itself. If it's union empty set is itself. So in this case, I get A union B. So that's the end of the proof. And of course, the last rule we use is identity. Okay. Now let's look at the next problem. I kind of butchered this question last time, so we're going to do it one more time. All right, so we want to prove if A is a subset of B, then A union B is equal to B. We're going to use, this is actually in part 1 slide. We're going to use a property we proved before, but of course in exams, if this is a non-standard property, you should prove it first. We're going to take advantage of that since we proved this earlier in the part 1 of the lecture. We want to prove A union B is equal to B. So we're going to start with the left-hand side, A union B. Because we have, since A is subset of B, A intersect B is equal to A. So we're going to use substitution of this part. So I'm going to replace A by A intersect B. All right, this is where I got stuck last time. So the first thing I'm going to do is I'm going to do some rearrangement, which is moving using commutative rule. So I'm going to move B to the left. And then also in terms of intersection, I'm going to move B to the left. So there's a bunch of rearrangement that just happened. Actually, I essentially applied this twice. Now what I'm going to do is I'm going to use absorption. All right. In fact, we're going to use the second part of absorption rule. Then I just get B, sorry. So the difficult part of this proof is really the last step, is using absorption, okay? And typically when you try to prove set relations, you're going to get things like absorption, De Morgan's law, and so on, okay? All right, let's do the next one. First of all, before we do more problems for proof of sets, let's go over the definition of a partition. So a partition of a set is a set of sets that has multiple sets as element, okay? So first of all, the first rule is that each of those sets has to be non-empty. Second rule is that if they're not the same set, they have non-empty intersection. Oh, sorry, they have empty intersection. Last one is their union has to be equal to the original set, which means that every element of A is in some part or in some of those set. Okay, so let's look at the first one. If I give you 3 sets, the first set is 2k, so k is integer, so A is actually the set of all even numbers. B is 3m plus 1, m is in Z, so B is really all the set of integers mod 3 equal to 1, meaning that when you divide by 3, it has a 1 as a remainder. And C is the set of integers when it's mod 6 has 5 as a remainder. We want to show that A, B, and C is not a partition of Z. So there's 3 things to check. The first one is each part non-empty? Okay, so that means each of those sets A, B, C have to have at least one element. The answer is yes, because for example, 0 is in A, 3 plus 1, let's see, 1 is in B, and of course 5 is in C. Okay, so none of those sets is empty, so that's good. Second property is asking, is each part, right, each of those sets disjoint? Okay, this is a time where you should pause the video and try to solve it on your own. The answer is actually no, because if you look at B and C, if I set m to be 1, then 3 times m plus 1 is equal to 4. 4 is part of B. But also, if I set k is equal to 2, then 2k is 2 times 2 is equal to 4. That is also part of A. So that means A intersect B is non-empty. So that means they are not disjoint. The last one is every element of integer in some part. So that means every single element in Z has to be covered by set A, B, or C. Is this true? This takes a little bit effort to look for essentially does there exist some element that is in Z but not in A, B, or C, okay? Of course, you have to be a little bit careful, so now let's think about it. First of all, the set A is set of even numbers. The set B, remember every element in here wins mod. Any element in B wins take the remainder is equal to 1. So it's not divisible by 3. And the last bit, we can probably write it as 6n plus 3 plus 2, which is 3 times 2n plus 1 plus 2. So this one means that if it's divided by 3 as a remainder of 2. So if you look at all these properties, something is missing, which is integers that is divisible by 3. It's not covered. So that means, for example, 3 is not part of A, and 3 is not part of B, 3 is not part of C. Similarly, 6 is not part of A, 6 is not part of B, 6 is also not part of C. Okay, so that means not every single element in Z belongs to A, B, or C. Okay, so there's 2 conditions that is not satisfied, which means, well, if one of them is not satisfied, it's already not a partition, but we're checking all 3 properties. Okay, the next one is we want to show indeed the set A and B is a partition of Z. If you look at it, the set A is a set of even integers. The set of B is a set of odd integers. So we really want to say that even and odd integer create a partition. Okay, so of course, the first thing is going to ask the same question is, as before, is each part non-empty? The answer is yes, because I can say, well, 0 is even number, 0 is in A, 1 is odd number, 1 is in B. So the set is definitely not empty. Now the next thing is each part disjoint? Okay, so now you want to prove that, if the element that is in A, then it's not in B. You can prove by contradiction. Okay, so what we do is suppose there exists some number x that is in A and is in B. So that means A and B is not empty, right? Okay, so now if it's in A, then it's equal to 2 times k for some k in Z. Because it's also odd, it's going to equal to 2p plus 1 for some p in Z. So now I have 2k equal to 2p plus 1 by substitution, and I use some algebra moving 2p on the left-hand side, so minus 2p on both sides of the equation. I get 2 times k minus p is equal to 1. So on the left-hand side, it means 1 can be expressed by the closure property of k minus p is an integer. So 1 is 2 times some integer. So it just says 1 is even, which is a contradiction. Okay, based on this expression. So that means there are no counterexample. That means original statement is true. That is indeed A intersect B is empty. Last one is I going to ask, is every element of Z in some parts? Element. Okay, so you want to consider for every element x in Z, you want to consider is either even or odd. Okay, so I'm going to skip this part, but just show you the actual proof in detail. We are at the last bit. Consider an element that is in the set of integers. We want to show it's either even or odd, okay? When it is even, by the definition of even, is equal to 2k for some k, so that means it's in set A. If it's odd, by the definition of odd, it can be expressed as 2p plus 1 for some p, which follows that it's part of B. Okay, so this is really by definition of AB. So this last bit is not that hard. Okay. All right, so now let's look at two last problems involving sets. One problem is to try to, both of them is actually try to prove by contradiction. The first one is prove that for all sets A intersect A prime, which is a complement, is empty, okay? So by definition, recall A prime is equal to universal set minus A, okay? So since we want to prove by contradiction, we want to assume there exists a counterexample. So suppose there exists a counterexample. All right. So that means there exists some element X, some set A, such that A intersect A prime is not empty. Okay. So because it's not empty, then there exists some element X that belongs to A, intersect A prime, okay? Since we want to prove by contradiction, by the way, this is just a sketch. If I want to prove by contradiction, we first assume that there exists a counterexample, which means that A intersect A prime is not empty, and the element, there exists at least one element X that is in the intersection, okay? So this means X is in A and X is in A prime, okay? When X is in A prime, this means X is in U minus A by substitution, which means X is in U and X is not in A. This is by definition of A prime, essentially. So now I get from the second part, I get X is not in A. From the first part, I get X is in A. So that means X is both in the set and not in the set. That is a contradiction. So that is X is in A and X is not in A. This is a contradiction. All right. Okay. So let's look at the next one. And this is the last question of today. And then I would suggest you turn off the video again and try to solve this on your own. And this will probably take 2 or 3 minutes. Okay. Let R plus to denote the set of positive real number. We want to show it does not have a smallest element. Okay, so what is a sketch? The proof sketch is again by contradiction. So we say that, well, we want to prove R plus does not have a smallest element, but let's assume there is a smallest element. So suppose exist element E that is in R plus, and that is the smallest. All right. However, if E is the smallest, we know that if I divide it by 2, because, well, first of all, E is positive real number, so E is bigger than 0, which means if I take E divided by 2, so inequality divided by a positive number is still positive. And we also have E over 2 is smaller than E, right? So half the positive number is less than the original number. So what do we have now is we have E over 2 is now a smaller element. And this contradicts the fact that E is the smallest. So this is a contradiction. Which means a counterexample does not exist and the original statement is true. All right, that is for part 2 of lecture 9. And then I will see you in next week's recitation. All right, have a good weekend.